Hello friends, welcome to follow up. So in the previous video we have worked on maximum binary tree 1, and in this video we are going to look at the second, right? This is problem 998. So in this video we are going to present and explain two formats of solutions. So both the two formats are based on recursion, and the first one is longer, which is meant to digest the details, and the second one is shorter, which is meant to catch the core logic. So here we are given the root of a maximum binary tree and an integer value called VAL. So we want to return a new construction of a maximum binary tree. We can imagine that, so in the given maximum binary tree, so that is the A here, it corresponds to a list or a array. So we want to append the value to the list, and then we want to return the new maximum binary tree corresponding to the augmented list. So that's basically the idea of the problem. So here are three examples. The first one is very easy to interpret because the value is larger than all the values in the nodes of the root, the tree given here. Therefore, the original tree will be the corresponding left subtree of node 5. So this is example 1. And in example 2, so the value is 3, right? So the 3 is append to the right, right? So it's going to correspond to the node 3 here. Example 3, so the value is here, and this is the corresponding tree, right? Originally we have 5 is the root, and the left subtree is constructed from 2, 1, and now the right subtree is constructed from 3 and 4, and the right subtree is corresponding to 3 and 4 because 4 is larger, so 4 will be the root of the right subtree, and then 3 will be the left subtree for sure. So this is example 3. So here again you can interpret this one, right? Because we appended 3. 3 is less than 4, so 4 remains the root of the right subtree for 5, and 3 also is to the right of 4, so it corresponds to the right subtree of 4 here in example 2. So with that said, basically we went over the 3 examples. So now let's look at the constraints. First, the number of nodes in the tree is not very large because the upper bound is 500. And secondly, the node value is in this range. This is actually not it plays some role because we need to make comparisons with the value appended. So this the values will be in between 1 and 100. Same for the value, right? It's in between 1 and 100. The thing is that all the values of the tree are unique. So this is an important assumption. In other words, both the given tree represented by root and also the new construct tree to be returned contain unique values, right? So that's also necessary for for maximum binary tree due to the construction procedure. So with that said, we are ready to look at the coding part. So actually for solving this problem, so we can write a very short code. However, here we want to demonstrate several things. First, due to the way of the maximum binary tree constructed, actually if we do in-order traversal of the maximum binary tree, it corresponds to the original array. So if you think we have such an array. So here first I'm going to write a in-order utility function. It's going to accept a root or tree node. So we're going to get the corresponding list or array. So if not root, So we're going to return an empty list. Otherwise, we're going to return, because we are going to use in order traversal. So we're going to first traverse the root left, and then we concatenate with the root value, and then we in order traversal the root right. So this, if we call this function, we're going to have the corresponding list for this tree rooted at root. So now let's see. We have the original list, so we can also append the value here in a verbose way. So we can have value, let's see, value appended. So it's going to be in order traversal, call this root, and then we can use a list concatenation, so we can have this value. So this list named value appended will corresponding to the new maximal binary tree we're going to construct. So now, as in the previous video for maximal binary tree 1, we can write such a function just to digest the detail. So we can write a build. So we accept an array, right? So then what we're going to do is that if not array, so we're going to return a null. So you can understand this null as a null tree node. So if the array is not empty, so we can call its largest value, right? So it's max array. And then due to the uniqueness assumption on the values, so we can find the corresponding index, that is array index. So we can call this largest. So if we can get its index, so we can use a left and the right. So originally empty list. So we find the left and the right part in the array, and then we construct the left subtree and a right subtree. So both are also maximal binary tree in themselves. So let's see, if idx is greater than 0, right? So we can update this left to be array up to this index, but not including the corresponding elements at index. Another one is that if idx plus 1 is less than or equal to n minus 1, and then we can update right? So array idx plus 1 onwards. So this check makes sure that this idx plus 1 is not out of range in indexing. So with that done, basically we can return the thing. So we can return the tree node. So this is the root. The value will be the largest, right? And the left subtree will be built from left, and the right subtree will be built from right, right? So this is a build function. Actually, this is identical in meaning as in the previous problem. So now what we're going to do is just call this function, do the return. So we are going to return build. So we apply this function to this augmented list. So this actually forms a solution format to this problem. So this code, actually, if we are clear about the logic, it's not very long. It's actually rather straightforward to write. So now let's first test. N is not defined. Okay, so let me change this to length of the array. Now let's check. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So this one basically is verbose, longer, right? Relatively longer, I would say. Just is meant to digest the details. So let me copy this function signature and write another solution. So here I'm going to call this one v1 so that we can test this function. What we are going to do is to use the definition of maximum binary tree and also the assumption that the values in the tree given and to the for the tree to be returned are unique. So due to this one, what we are going to do, so first we can see, we can consider one case if the value is very large, right? Because if it's larger than the root value, then as in example 1, so the because the value is appended to the tail, right? So it's the original tree will correspond to the left subtree of the node with value being this value, right? So now let's first do this. If root, so let's first make sure it's not null, and then the root value is less than. So the root value, let's see, we can check if it's larger than the value. So in this case, the root will remain unchanged for the tree even after we append this value, right? And then what we are going to do, we are going to do this. We are going to set root right, because the left tree does not change, right? Because the reason is that we append the value to the, you can imagine, to the tail of the corresponding list to the tree root. So what we're going to do is we call this function itself, right? And then so it's root right, and then we use this value. So this is one case, and then other case is that, so if not, so the we're going to have either null, right? This is done, and or base case, or the root value will be strictly less than the value due to the uniqueness assumption. Then we're going to make a new node, that is tree node, and then we're going to so the value will be the value, right? And then the left subtree will be the original tree, right? So we just need to return node in this case. Don't forget here we need to return root. So this is another solution format based on recursion, right? So you can imagine this non-root case is a base case. Also, this one is also a simple case. In other words, if the root value is smaller than the value appended, right? And then we do the recursive call here. So before we end this video or make 4 comments, let's first do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes the generic case. So with that said, that's about it for this specific problem. So here we give 2 solution formats. The first one is verbose, is to understand the details, and the second one is shorter and to utilize the call logic. So both are based on recursion due to the tree data structure. So with that said, that's about it for this video. Thank you.